All right, I just want to rehash very quickly the things that we did in the last video. A was taken to be this matrix as an example. Note that A is symmetric, meaning its transpose is itself. We found, by solving the characteristic equation, two eigenvalues. One is -1, and the other is 2, and this eigenvalue of 2 was repeated. It showed up twice as a root in the characteristic equation. We did the work of figuring out the first eigenvector, meaning the one corresponding to lambda 1, and we found that one of them, there are infinitely many, but one of them that worked is 1, 0, -√2. So now, we want to determine the second eigenspace, meaning E sub lambda 2. Remember, this is going to be the set of all vectors for which A is what I called the matrix, I think. A v is equal to lambda 2v. And remember, lambda 2 is really just the number 2. So we're just trying to figure out, I don't want to overcomplicate things. We're trying to figure out all the vectors that get doubled by A. Okay. So let's have a look at this. We want to solve A minus 2I v is equal to 0. Right? This is how we figure out all the stuff in this eigenspace. When there's only one of them, right, when we expect to only find one vector, we just call it an eigenvector, and we're done with it. This one is going to be more complicated. This is going to be an eigenspace. It is going to be a multi-dimensional thing that we are going to come up with. Okay, so we want to solve this. We know what A is, right? It was right above. So let me just solve A minus, or simplify rather, A minus 2I. That is going to be -1, 0, √2, 0, 0, 0, √2, 0, -2, applied to the vector ABC. That's what I'll call the components of V, set equal to 0, 0, 0. All right, so multiplying this all out gives you a system of three equations and three unknowns. Minus A plus √2c should be 0. The middle equation is just solid zeros, right? 0a plus 0b plus 0c equals 0. That's not the most informative thing you've ever seen. And the third equation says that √2a minus √2c, I'm sorry, minus 2c should be 0. All right, and again, I want you to recognize that, first of all, this system is degenerate because, or not degenerate, this system has infinitely many solutions because of that middle line right there. Right, that is giving us, it's eliminating one of the unknowns here. So one thing to notice here is that you only have two equations in two unknowns at this stage. B has disappeared entirely, right? B is not accounted for anywhere. So B is actually completely free. Right? It doesn't show up in any one of the equations that are left. So B is completely free. The other thing I want you to notice is that these two equations are actually redundant. They say exactly the same thing. So to see this, for instance, multiply this first equation by -√2, and you will turn it into this second equation. All right? So this is actually a redundant system, right? In even beyond that middle equation just completely disappearing and B being completely free, the resulting system of two equations and two unknowns is even further redundant, right? It's got redundancy built into it. So what this means is that we are only going to have, we're going to have 2 degrees of freedom here. B is free, and then one of A or C will be free, depending on how we arrange it. Right? That's what this why I'm harping on this redundancy aspect. That's why. It's because one of these remaining variables will still have to be free because this 2 by 2 system that's left is still redundant. So I'll work with this first equation, which tells me that A is equal to root 2c. All right, so the two variables that I'm going to have be free here are B and C. Those are going to be my free variables. And so everything in this eigenspace, right, E sub lambda 2, which is the set of all V's such that AV is equal to 2V, well, what we just discovered is that this is the set of all vectors that look like, let me go back and see what was free, C was free and B was free. So this is going to be, and A was root 2C. So this is going to be root 2C, B was free, C was free. And here, the only requirements are that B and C are just, scalars. All right, so the thing I want you to notice here is that because we have 2 degrees of freedom, B and C, this is a 2-dimensional beast that we're looking at. This is a 2-dimensional object that we are considering. It is a 2-dimensional vector space. So, we could figure out a basis for this thing. It is not the hardest thing in the world. You can do this in a variety of ways. You could just go ahead and pick some arbitrary values for B and C. Some like simple values for B and C, and see what vectors you get. This is one way that you could go about this. And there are some other ways that you could do this. I'll start by just picking arbitrary values, simple values for B and C. So maybe I'll pick B and C to both be 1 first, and that will give me, I don't have a great notation for this, I'll be honest, V lambda 2, and maybe I'll call the other one, let me call this one U lambda 2, and the other one V lambda 2. No, I don't want to do that. Let me call this one V and W. How about that? So V sub lambda 2, which is coming from my choice of B and C both being 1, will be root 2, 1, 1. All right? And let me call the other one W sub lambda 2. And I need other choices here. I don't know. Maybe B is 0, C is 1. Right? Maybe this will work. I don't know why I said maybe. This will work. Let's just look at it. We would have root 2, 0, 1 in that case. All right, so these are my 2 distinct eigenvectors. And these are linearly independent. This is easy to check. Just eyeballing it, you can see that they have to be, because this one has a 1 in the second component, and this one has a 0. So and since there's only 2 of them, they've got to be linearly independent. They cannot be constant multiples of one another because of that fact. All right, so V lambda 2 and W lambda 2 form a basis. For E lambda 2. Now, why I am making a big deal out of this is because of the following. Recall that lemma that we spent most of the last video talking about. Right, this lemma that I went through and I sketched the proof for it. I provided almost all the details. Said that eigenvectors to distinct eigenvalues should be orthogonal to one another if the matrix is symmetric. Okay, so we have this lemma in the back of our mind that says eigenvectors to distinct eigenvalues of A are orthogonal. So let's go ahead and check that out, right? Let's check that out right now. Right, let's just make sure that we're still sane. So what I'm asking here is you want to look at v lambda 1 dotted with these two eigenvectors that we just chose. V lambda 2 would be the first one to check. Right, so this is v lambda 1. It's on the last page, I think. I wrote it down. Whoops, I think I wrote it down. Yeah, 1, 0, negative root 2. V lambda 2 is right up here. That's this one. So that's root 2, 1. Whoops. Root 2, 1, 1. And notice that this is root 2 minus root 2. This is 0. They are indeed orthogonal. Let's check the other one. All right, we also have w lambda 2, this other eigenvector. And let's check this other one, v lambda 1 dotted with w lambda 2. Well, this is v lambda 1 is right there, dotted with w lambda 2. That was the second eigenvector, root 2, 0, 1. Whoops. 0, 1. And this again is root 2 minus root 2, which is 0. So that's great. Now, I promised you that we would be able to find an orthonormal basis of eigenvectors for A. So it looks like we're on a good path here. It looks like we've got v lambda 1 that's, right, v lambda 1 is orthogonal to both v lambda 2 and w lambda 2. So this is looking good. We have one more thing to check if this forms an orthogonal basis, and that is to check the orthogonality of these two fellas. And just eyeballing it, hopefully you can see that those are not orthogonal. Let's go ahead and check. All right, so if we check the orthogonality of v lambda 2 and w lambda 2, right, so these are two eigenvectors corresponding to the same eigenvalue, which our lemma said nothing about. This is root 2, 1, 1, dotted with root 2, 0, 1. And this is going to be 2 plus 1, which is 3, not 0. So, what we have right now is a basis of eigenvectors. All right, so let's summarize what we have. That was terrible. Terrible ellipsis. There we go. So, we have v lambda 1, v lambda 2, w lambda 2. This is a basis for R3. But it's not an orthogonal basis. So, we need to think about how to fix this. All right? Well, I've given you a basis. Right there. It's got 3 vectors in it. How can we fix, so to speak, a basis that we want to be an orthogonal basis? We've seen a way of doing this. I made you do at least a few examples of it. All right, so take a minute, think about this. How do we take any old basis and soup it up to become an orthogonal basis? Think about that and try to come up with an answer for this, all right? Pause the video if it's not coming to you right away. And hopefully, after not too much time, the answer should come to you. This is why Gram-Schmidt exists. This is why the Gram-Schmidt algorithm exists. However, we need to be really careful about how we choose to implement this, right? In this specific example, what I'm about to say is not going to matter, but we should make sure that that we are being careful when we do this. All right, so what I'm trying to get at here is that we don't need to apply Gram-Schmidt to all the vectors in this basis. All right, notice that in terms of orthogonality, v lambda 1 is already orthogonal to both of these. So v lambda 1 relative to the other two vectors is not the problem. All we need is to force these two to also be orthogonal. That's where our problem exists right now. Okay, so the way that we're going to do this is not by doing Gram-Schmidt on all three vectors together, because not all three vectors are a problem for us. We're only going to do it, right? You never want to do more than you have to. Save time and effort whenever you can. So if you can put a few seconds of thought or a few minutes of thought in at the beginning, and it saves you a lot of time down the road, well, that's great. You should do that. All right, so what we're going to do here is apply Gram-Schmidt only to the eigenvectors, to the vectors that exist inside of this eigenspace E lambda 2. We want to orthogonalize stuff just living in that space. And then, once we do that, just by accident, because v lambda 1 is already orthogonal to everything in E lambda 2, well, we'll be done. All right, so we want to use that lemma from the last video to our advantage, and just be strategic about what we actually orthogonalize here. It won't actually matter if you did go ahead and try to orthogonalize all three at the same time, because there's already some orthogonality built in. You'd end up getting the same thing anyway. But, you know, why do more than you have to, especially if you've got more vectors than just three. All right, so we are going to apply Gram-Schmidt just to v lambda 2, w lambda 2. All right, we really just want to orthogonalize those. So I'm going to have, and again, I don't have great notation for this. I'm very sorry about that. Let me not call it u. Let me call it, I don't know. I'm hesitant to use Greek letters because they scare some people. So, you'd think I could come up with better names. Let me call them, screw it, I'll just use Greek letters. Alpha, no, that's terrible. Let's just call them U1 and U2. How about that? We're all adults, we can handle this. All right, so U1, we are going to take to just be v lambda 2 left alone. All right, remember this is how Gram-Schmidt begins. This is the vector root 2, 1, 1. And U2, we take to be the second vector, which is w lambda 2, minus the projection onto v lambda, I'm sorry, onto, mixing my notation here, onto U1, which is v lambda 2, of w lambda 2. All right, this is how Gram-Schmidt works. So w lambda 2, this is root 2, 0, 1, minus the projection onto U1 of w lambda 2, so that's going to be root 2, 1, 1, dotted with root 2, 0, 1, over root 2, 1, 1, dotted with root 2, 1, 1. And this is going to be in the direction of root 2, 1, 1. All right, so just, brute forcing our way through this. We'll have root 2, 0, 1 minus, now upstairs, right? Just this part, we will have root 2 and root 2 plus 1, so that's 3. Downstairs, we've got 2 plus 1 is 4. Root 2, 1, 1. All right, so this is root 2 minus 3/4 of root 2 is 1/4 of root 2. Minus 3/4. Downstairs, we've got 1 minus 3/4 is 1/4. I'm just going to factor a 1/4 out of that. This is root 2 minus 3, 1. All right, so that is u2, is this vector 1/4 of root 2 minus 3, 1. All right, so we've got u1, which is root 2, 1, 1. u2 is 1/4 of root 2 minus 3, 1. Now, these two are orthogonal because of the way Gram-Schmidt works, and indeed, both of these still live. Right, this one never left E2 because it was just left totally the same. This one also lives in E lambda 2. And the way we know that is because we knew that the original two vectors were a basis for E lambda 2. And remember, this property of Gram-Schmidt says that in Gram-Schmitting things, you don't change the spans as you move through the algorithm. So the span of U1 and U2 will be the same as the span of the original two vectors, v lambda 2 and u lambda 2, v lambda 2 and w lambda 2, I think I called them. In other words, it will both, the span will still be e lambda 2, right? The span hasn't changed. In other words, u1, u2 is now an orthogonal basis for e lambda 2, and v lambda 1 was orthogonal to everything in e lambda 2 to begin with. So it's now going to be orthogonal to u1 and u2. Right, so summing this up, the basis v lambda 1, u1, u2 is now an orthogonal basis for R3. And, moreover, consisting only of eigenvectors for A. All right, this is pretty incredible. This is, if you remember back to when we were doing all that vector calculus stuff near the beginning of the semester, we sort of talked about like these space curves that are flying around in space. And at any given point, I mentioned that there's these like three principal vectors associated to any space curve. Right, so if we look at a point, let's say right here, well, one of the vectors which we used a lot is the tangent vector. Another one, which comes up pretty frequently, is what's called the normal vector, which is orthogonal to that one. And then the third one, which we didn't talk about at all, but it comes up a lot in Calc 3, is a third orthogonal vector called the binormal vector. And, the idea here is like, as a fly flies around the room, its frame of reference for the room is a little bit different than yours if you're just sitting still, right? At any given moment in the fly's path, forward will be its tangent vector, and it cares about that vector because that's the direction it's moving in. Either its left or its right or something will be the normal vector, and then either up or down will be its binormal vector, right? Something like this is the rough intuition. And it cares about those things because as it's flying around, it needs to know what is up relative to it, not what is up relative to you sitting in your comfy chair or laying in bed, right? So this is why these three vectors matter. And these three vectors are really how the particle flying on its path, or the fly flying on its path, it's its frame of reference for the space. Now, why I'm mentioning this is because what we've just said here is that notice that n, t, and b form an orthonormal basis for R3, and what we just said here is that this symmetric matrix has an orthogonal basis consisting only of eigenvectors. So this is like how the matrix, so to speak, A, sees the space. Right? This is sort of what this means. These are the three characteristic vectors on which A just looks like constant multiplication, and it forms an orthogonal basis for R3. Right? So in a sense, this is like how the space is framed by this symmetric matrix A. Right? In the same way that N, T, and B frame the space for the fly flying around the room, or the airplane flying around space, or you on a roller coaster, or whatever, right? Your frame of reference changes from moment to moment. Well, the same idea here is that this matrix A has an orthogonal basis of eigenvectors, which sort of frame how it exists in R3. Right? And this is really the important part of why we're going to talk about this. And what this leads us to is actually sort of understanding what happens to A, the matrix, when we choose the basis for R3, as opposed to consisting of the standard unit basis vectors like 1, 0, 0, 0, 1, 0, 0, 0, 1, how we almost always do. What happens if we instead choose the basis that consists of its eigenvectors? What does that do to sort of the behavior of A? All right, so you can think of this like putting yourself in A's shoes, right? What happens if you see the world through A's eyes, as opposed to seeing it from your eyes, which are rooted at the origin, looking straight ahead, if that makes sense? Right? Don't view it the way you view it standing still. Instead, view it the way that A does, right? Just like, the fly flying around your room. Well, look at the room through the fly's 1,000 eyes instead of your own stationary eyes, and you'll see things a little bit differently, right? So this is kind of the idea. It's where we're headed. What does A? That's the big question that we want to answer next. What does A look like? Put that in quotes, because what does that mean? Relative to this basis, this orthogonal basis of eigenvectors. All right, so this is where we are headed next.